We're going to pick up here at the bottom of the second page of your notes and do example number, it's number 7 from page 277. So it says we have a graph of f of x equals 2x minus x squared. And this question we've been told is going to refer to the region R, which is enclosed by y equals 2x minus x squared and the x-axis between x equals 0 and x equals 2. So part A is to make a sketch. So I hope this is in your skill set here. You can make a table of values. You might only consider x values between 0 and 2, since that's the part of the graph that we've been told is going to be important here. My technique probably is to notice I can factor this. And that tells me that I'm going to have zeros. This is going to be a parabola because the degree is 2. It's going to have zeros at 0 and 2. It's going to be a parabola that opens down because the coefficient on the squared term is negative. So the one other thing I might want to do is figure out the vertex. Well, the vertex is going to be halfway between the two x-intercepts. So that's x equals 1. I might say when y equals, what is y when x equals 1? That's going to be 2 times 1 minus 1 squared, which is 2 minus 1. So I'm going to have a vertex, of 1 comma 1. This is a parabola that opens down. All right, and then part B says, partition 0 to 2 into 4 subintervals and show the 4 rectangles that LRAM uses to approximate the area of R. So we're going to compute this compute that approximation, that LRAM approximation, without a calculator. So I'm supposed to take the distance between 0 and 2 and split that up into 4 smaller rectangles. Well, I'm going to have, if I have a total width of 2 that needs to get broken up into 4 sections, then each section is going to be a half wide. So I'm going to have one rectangle cover from 0 to 1/2, another rectangle from 1/2 to 1, another rectangle from 1 to 1/2, from 1 to 1.5, and then from 1.5 to 2. So I might make a table of values. 0, 1/2, 1, I'm going to call that 3/2, and 2. I know that's 0, I know this is 1, I know this is 0. So I'm going to replace x in my original rule with 1/2. That's going to be 1 take away 1/4, which is going to be 3/2. 1 take away a 4th, which is 3/4. I could use symmetry to figure out that this is also going to be 3/4. So I've been asked to show the rectangles for LRAM. That means I'm going to have my rectangles touch at their left-hand corner. So I'll use green here. So my rectangle that covers from 0 to 1/2 is going to have a height of whatever f of 0 is. Well, f of 0 is 0. So that's my first rectangle. It happens to be height of 0. My second rectangle is going to cover 1/2. The x value is 1/2 to 1. And it's going to have a height of 3/4, which is going to be this. My next rectangle is going to have a height of 1 and cover from x equals 1 to x equals 3/2. And then my last rectangle is going to have a height of 3/2. So my last step is to compute the LRAM approximation. That means I'm going to find the areas of those 4 rectangles and add them up. Well, so I'm going to write LRAM. Every rectangle has a width of 1/2, so I'm going to multiply 1/2 times the first height is 0, plus 1/2 times the second height is 3/4, plus 1/2 times 1, plus 1/2 times the next rectangle has a height of 3. That last rectangle has a height of 3/4. So I have lots of options about how to simplify that expression. I've been asked to compute it without a calculator. Notice I could factor the 1/2 out and then add 3/4 and 3/4 and 1 to make 1.5. 2.5. So 2.5 times 1/2. Or I can multiply it. It's not a big deal, however you choose to do it. So that's what I'm going to do. I'm going to think of that as 1/2 factored out. I'm going to add 0 to 3/4 to 1 to 3/4. That makes 6/4 and 4/4 is 10/4, which is 2.5. Which I'm going to multiply by 1/2. That's an equal sign. 1.5 times 2.5, which is going to be 1.25. When you get down to the exercises at the end of this handout, you're going to be asked to do question 8, which is the same problem, but you're going to use RRAM and MRAM. It'll be a good exercise to think about how your answers compare. So new important word for us, Riemann sum. Anytime you use rectangles to approximate area under a curve, we call that result a Riemann sum. Notice that includes LRAM, RRAM, MRAM, and any other kind of rectangles you might use. Although these are the 3 you would be expected to know for the AP test. Obviously, it's going to be very rare, it would be almost a miracle, for just coincidentally that to be the exact value of the area under the curve. You could think about one place it would happen, though. See if you can think of that. So we want to start to think about what kind of errors am I going to have? What kind of differences will I have between the actual area under the curve, which I'm going to learn how to compute with calculus, and my Riemann sum approximations. So 2 types of errors we can be totally sure of. If I try to find, the area or approximate the area under F, and I know F is increasing, and if I use left-hand rectangles, I'm going to have an underestimate because every rectangle is going to fall underneath the curve. I'm going to have space every time. If I have an increasing function, but I use right rectangles, let me change color. Right rectangles, I'm going to have an overestimate. And the other way around, if I know F is a decreasing function and I try to approximate the area under F with LRAM, then I have an overestimate. If I try to find the approximate area under a decreasing curve with RRAM, I'm going to have the overestimate. See that right? It's in your notes. The notes are right. So let's think about this example. I have a rocket. It has a positive velocity, and I'm missing my little left center equal to signs, but I know some things about the velocity of the rocket from time 0 to 80. So use MRAM with 3 subintervals to estimate the distance traveled by the rocket from time 10 to 70. And I'm supposed to indicate units. So notice they've told me exactly how many rectangles to use. So 3 subintervals means 3 rectangles, and they should cover from time 10 to time 70. So this is what I would do. This is probably what you'll find every calculus teacher would tell you to do. From 10 to 70, that's a difference of 60. And if I need to fit 3 rectangles in there, 60 divided by 3 makes 20. So each rectangle is going to be 20 seconds wide. That means my first rectangle is going to cover from 10 to 30 seconds, my second rectangle from 30 to 50, and my last rectangle from 50 to 70. So now I know how many rectangles I need and what time values they're going to cover. I need to figure out how tall each of my rectangles should be. Well, here they've specified I'm supposed to use MRAM. That means I'm going to look for my rectangle that covers from 10 to 30. I have to think of what's halfway between 10 and 30, 20. And I'm going to use the output value when the input is 20. So when t is 20, v of t is 22. So each of my rectangles is 20 wide. So it's going to be 20 times the height is 22 plus my next rectangle is also 20 wide, and its height is, well, it covers from 30 to 50. Halfway between 30 and 50 is 40. So I find the output when the input is 40. 35 plus here. So it's 60. My output is 44. So that's going to give me the number part of my answer. Now I have to think about the units. Every time I was multiplying a distance across my rectangle, this 20, notice that 20 was the difference between these 2 time values. So my units are going to be the time units, which is seconds. Let me do this. Times the heights, I were using the 22, the 35, and the 44. They're all velocity values, and velocity is measured in feet per second. So it's going to be seconds times feet per second. And I suppose you could leave your answer like that, but we're going to class it up a little bit. This is going to be 440 plus 700 plus 880, which is, does it end up being 2020? Seconds times feet per second is feet. So you can see we're going to ask the same kind of question, use the same kind of table. They might ask for a different type of rectangle. So let's clear this out. And this time I'm going to use RRAM with 2 subintervals of equal length to approximate the distance traveled from 0 to 20. So from 0 to 20, I need to fit in 2 rectangles. So I'm going to have one rectangle cover from 0 to 10. Oops. 0 to 10. And the second rectangle from 10 to 20. So here, the width of my rectangle is 10. What height should I use? Here it says RRAM. So for the rectangle that covers from 0 to 10, I want to think about the right-hand edge of that. The right-hand edge is the 10. So I'm going to use the output value when the input is 10. So 10 times 14. Plus the width of my second rectangle also is 10. That's the difference between the 20 and the 10. And the height at the right-hand edge is going to be the velocity at the right-hand edge, which is 22. Same units as before, that's going to be seconds times feet per second. So I'm going to have 140 plus 220 equals 360 feet. And then here's the big question. Is my answer an overestimate or an underestimate of the true distance traveled by the rocket on that interval 0 to 20? Well, now I have to go back to find out if I know about the increasingness or decreasingness of the velocity. So now I'm going to read back here. Oops. So rocket A is a positive velocity. And that velocity is known to be increasing. So now I have enough information to finish the second half of part B. If V is increasing, and I used RRAM, you can use this little picture that I drew to remind you of why my estimate is going to be an overestimate. In my head, I'm thinking, hey, look, every little rectangle is above the curve, so every time I use a rectangle as an estimate of a piece, I'm using an estimate that's too big. But the answer you're going to give has to go like this. So I'm going to say 360 feet is an overestimate of the distance traveled on the interval, on the time interval, what was it, 0 to 20 seconds, because, V of t is increasing and R RAM was used. So it's not your job to say that you drew a little sketch and you know that every rectangle is too big. You know because the function you were trying to find the area under, V, is increasing and you used RRAM, and RRAM always overestimates for the area under an increasing function.